Whenever you estimate, you'd like one of the reasons you estimate is because you think that you're going to get close to the actual value, and moreover, you want to know and you should be able to measure how close you are. Taylor's theorem tells us how to do that. I'm going to state what Taylor's theorem is and try to make sense of some of the symbols here. In particular, the Lagrange form of the remainder here. Looks particularly intimidating, but we'll work out an example or two of using that. Taylor's theorem says that if f of x has at least n plus 1 derivatives, on some interval containing a center point, containing a center point C, then the polynomial not only is close to this recipe for Taylor, but it's exactly equal if you take into account an error or what's called a remainder term. More specifically in symbols, I would say that says that this function is exactly equal to the nth degree Taylor polynomial using the same recipe that we did above, plus a remainder term of degree n. And the remainder term is written like this, of x centered at C, so x colon C, where this remainder term is the Lagrange form. Remainder. So this is saying that our approximations are good, and they're all going to be then the most that the Taylor approximation and the actual function itself are off by are given by this remainder term. This remainder term has a formula that looks like this. It looks a little intimidating, and I'll try to explain what some of the notation really means, and we'll put it into action to see kind of how to actually use this. But the Lagrange form of the remainder for x centered at C is given by this formula. It's at most the absolute value of the n plus first derivative of some other value, we'll call it z, over n plus 1 factorial times x minus the center to the n plus first power, all in absolute value. Note that this is just this has the very similar structure to what just the next term in the Taylor polynomial would be. Only what's kind of odd is that there's this z in here now instead of the center term. This z where z is some number that's between the value of x you're approximating at and the center. So z, if you think of a number line, that this that our center of the polynomial is some value c. X's can be either to the right or to the left. Can either be somewhere to the right or somewhere to the left of c. Like either x could be to the right of or maybe x is to the left of. And this is saying that z has got to live somewhere between wherever you choose x and the center point. So z lives in here. It's some value in here. Or if x happens to be less than the center, then z lives correspondingly in here. We'll use this in more so to approximate the largest that this error or this remainder could ever be. And that's going to tell us, help us answer questions like be able to show that our estimate is within a certain number of decimal places of the actual value. So let's try to complete a couple examples, or at least one example here. I think I have two. Let's start by finding a third degree Taylor polynomial sine, and we're going to center it at pi over 4. So let's see, just as we did before, sine. If we're centered about pi over 4, this tells us that c is pi over 4. So if I need the third degree, I'll go to x to the third term. I need to know the value of my function at the center. Sine of pi over 4 is root 2 over 2, or how about just 1 over root 2? Unrationalized. The first derivative of our function, derivative of sine, is cosine. And the derivative at the center point is also 1 over root 2. The second derivative of cosine, is minus sine. So the second derivative, well, my handwriting is getting worse, pi over 4 is minus 1 over root 2. And the third derivative is minus cosine. So the third derivative at pi over 4 is minus 1 over root 2. Put this together, in our third degree Taylor polynomial then is going to be equal to the function at the center plus the first derivative over 1 factorial times x minus the center plus the second derivative over 2 factorial times x minus the center squared plus the third derivative over 3 factorial times x minus the center to the third power. Or each term has this 1 over root 2. Maybe I'll write this a little bit, I'll factor that out to make this a little more legible. I'll factor out the 1 over root 2 to make this a little bit easier to read. 1 over root 2 about 1 plus 1 over 1, or just x minus pi over 4. Factor out the 1 over root 2, so there's a minus 1 over 2 factorial, or minus 1/2 x minus pi over 4 squared. Factor out the 1 over root 2, so there's a minus 1 over 3 factorial. The third power. Ideally, you could write this on one line, but I was kind of cramped for space. Part B, this is easy. Part B says use this to estimate the value sine of pi over 5. Well, sine of pi over 5 is approximately our Taylor polynomial when I plug in pi over 5, which is simply replacing all the x's with pi over 5. So I did that, typed that in my calculator, and I got the following decimal, 0.5878. Again, by replacing x's with pi over 5s. Lastly, part C says, now use the error term to show that this estimate is good to at least 3 decimal places. What that's telling us is we need to calculate what the error term is, what the value of it is, and hopefully that error term it'll be so small that when we add it, it will not affect the third decimal place. So let's get an estimate on its size. The remainder, after an approximation of 3 of this value of the value x equals pi over 5 when we're centered at pi over 4. So it'd be the notation x colon c. Let's fill in what this remainder, the definition of the remainder term. This says that this is the fourth derivative of our function when I plug in some z, and we'll remind ourselves what z means in a second, over 4 factorial times x minus c to the fourth. Well, x is pi over 5. C is pi over 4. So the fourth power. And our remainder term is going to be have size of this. And recall that z is between x and c. So z is some number between pi over 5 and pi over 4. Okay. We don't know how to compute this because we don't even know what z is, but we can estimate how big this is because we can calculate what form the fourth derivative of this function is. The fourth derivative of sine is, well, also sine. Note that the fourth derivative of my function is sine. So the question is, what's the largest that sine of x will ever be? Specifically in the interval between pi over 5 and pi over 4. But more generally, the maximum that sine ever gets, the max of sine is 1. Sine never gets bigger than 1, no matter no matter what input you choose. So I think because of this, I could estimate this term, this fourth derivative of z, that this is going to be, this is definitely smaller than 1. Meaning that this remainder, the third degree of this remainder, is no bigger than if I replace this term that has a z with this way easier to deal with term that's just simply 1. 1 over 4 factorial times pi over 5 minus pi over 4 to the fourth power. This is just a number. I can figure out what this is to the fourth power in my calculator, divide it by 4 factorial, and it turns out that this value, according to my calculator, is 0.0000254. Meaning the furthest away that my estimation, when by using my polynomial and plugging in pi over 5, the worst this approximation is to actually sine a pi over 5 is being off by this much. Specifically, the third decimal place will never be impacted because this value is just too small. So the estimation of the Taylor polynomial third degree at pi over 5 is definitely good to 3 decimal places, and actually it's good to 4 decimal places too. Because the remainder is so small.